chemical reactions that are exothermic, heat given off, and then we have reactions that are endothermic, where heat is absorbed. It's important in chemistry to realize that there's really no such thing as cold. There's cold, and you say, well, sure there is. I've been places where it was really cold, and I've touched things that are really cold, but you know, I may have even put my tongue on a frozen flagpole and said, that's really cold. But the thing is that in science there is no such thing as cold. Cold is actually the absence of heat. Your refrigerator actually pumps the heat out absorbed into the Freon, takes the heat out, and then blows the heat out. So remember, there's no such thing as cold technically in chemistry. Cold is actually the absence of heat. So when we create heat, heat is given off, okay, that's exothermic. So that's a warm reaction. You know, we go when we buy an instant heat pack, we break it, it causes an exothermic reaction. Oh, then we go and buy a cold pack, and it's endothermic, and it feels cold, but what it's actually doing is it's removing the heat. Heat is absorbed into it, causing it to be cold. Well, as we move into temperature, we have three main temperature scales. We have the Celsius scale, the Fahrenheit scale, and the Kelvin scale. Now, the Celsius scale is the metric unit scale that we use in this class. We also use the Kelvin scale. We'll talk about that here in just a little bit. The Celsius scale, water freezes at 0 degrees. Water boils at 100 degrees. We love that. Easy calculations. Once again, everything is from 0. So when we do the Fahrenheit scale, okay, that is our English unit. And once again, you know, we've talked about this a little bit before, but the English units are not really logical, but they're what we're used to. You know, ounces, gallons, pints, quarts. You know, I know when I was growing up, my dad said, "Oh boy, you know, we've got to practice this. How many ounces in this? How many pints in a quart, and all these different things." Well, now we're getting to where we're even getting away from those, because in chemistry we can't use the Fahrenheit scale, but that's our comparison. So for us in our regular scale, you go outside and you see the temperature out there, and 32 degrees is freezing, okay, where water freezes in the Fahrenheit scale, and 212 is where water boils. So once again, we see this, but disregard this for chemistry. You want to stay with the Celsius scale. But we want to go to one more scale now, okay? We want to go to the Kelvin scale. The Kelvin scale is a very significant scale for chemistry, okay? Because what Kelvin is water freezes at 273 K. But let me tell you what the Kelvin scale is. The Kelvin scale is where we try to reach, okay, 0 Kelvin, all right, 0, and we don't even put degrees because it's so hard to measure that we can't even tell you it's exactly, but 0 Kelvin equals absolute 0. So 0 Kelvin equals absolute 0. What is absolute 0? Absolute 0 is where the molecules stop moving. Molecules stop moving. Now, that sounds simple, and it sounds like, okay, well, let's just go to 0 K. Let's just make absolute 0. Well, this has actually only occurred a few times. Okay, actually only occurred a few times in the history of man. We can't get those electrons that are traveling 186,000 feet per second to stop. So when we slow those electrons down, and in this class we're going to use a lot of application of absolute 0, then we have no way to measure that. So then we come in with the Kelvin scale. So water freezes at 273 K. If I say to you later on in the class that something is 10 K, then you're like, oh my gosh, that means the molecules have almost stopped moving. That's significant. So you will see a lot of things measured in Kelvin, but it's so hard to measure that we don't even use the degrees. Now sometimes you will see people put a degree on there, but chemists don't generally put degrees because it's so hard to measure. We don't even know water boils. That's not even significant for the Kelvin scale, because we're more concerned with absolute 0, the point at which the molecules stop. Now, I do want to talk to you a little bit about, we talked about the words earlier, but once again, these are the basic spellings that we use for Celsius and Fahrenheit. But if you see different spellings, remember there's the original words, and remember they've gone through the English system. And remember, only in America can we just change words to fit them the way we would like for them to be. But these are the accepted words here. But when you see others, it's because they're the original Latin words. So once again, three main temperature scales. You're going to need to know these. And temperature at which water freezes and water boils. remember the Kelvin scale, but I want you to know that the Kelvin scale is also known, okay? Remember, Kelvin is equal to absolute zero, so the Kelvin is also known as the absolute zero temperature scale. All right, just to remind us there, the absolute zero temperature scale. All right? So once again, the Kelvin scale is also known as the absolute zero temperature scale. What are we worried about with Kelvin? Molecules stop moving. Electrons stop moving. Very significant chemistry thing. So now we begin to talk about heat transfer. We talk about calories. Oh, man, in our day and time, calories it's an interesting deal. Like, how many calories do you get from this amount of food, or that amount of food, or this substance, or that substance? Well, calorie is actually defined as the amount of heat needed to raise 1 gram of that substance 1 degree Celsius. So, once again, a calorie is the amount of heat needed to raise 1 gram of a substance 1 degree Celsius. So, we say that we're out working and we're doing things, we're burning off calories. Basically, we're determining in terms of the cells in our body and the intake we take in food, how much energy does it take to raise 1 gram of that particular substance, whatever it is. If it was carrots, or it was a Rice Krispie treat, or it's back to that pineapple upside down cake, what are the calories? Well, it's the amount of heat needed to raise 1 gram of substance 1 degree Celsius. Now that definition is also known as, and on your test I'm going to ask you both, I'm going to say, what's a calorie? And then I'm going to also say, what is the specific heat of a substance? Well, it's the same definition. The specific heat of a substance is the amount of heat needed to raise 1 gram of that substance 1 degrees Celsius. So now we're going to look at a formula here. We're going to tie this in because I'm fixing to show you a calorimeter, and I'm fixing to show you how chemists actually calculate how many calories there are in things. And this is significant as we move on in chemistry and we determine energy and we account for where the energy has gone and the form it's in and where it's going. Okay, so the formula for amount of heat transferred, okay, heat transferred is equal to the mass of the water, the weight of the water, times the change in temperature, times the specific heat of water. Now, the value for the specific heat of water is 4.18, okay? So you'll need to know that. Now, 4.18, when we talk about the specific heat of water, it's kind of interesting because we say, what's the specific heat of a substance? Well, specific heat of a substance is the amount of heat needed to raise 1 gram of a substance 1 degree Celsius. So how much does it take to raise 1 gram of water 1 degree Celsius? Well, it takes 4.18 degrees Celsius. Oh, interesting. So here we go. So this is the specific heat of water. Now, let's go to a calorimeter. This is the actual chemistry equipment here that we use to determine calories. Well, the first thing we have is we have a container here, okay? So we'll draw these in our notes, and you'll have to draw this on your next test. So we've got a container here that's going to hold our water and hold our sample here. But then it also has to be insulated, okay? It also has to have some insulation in here, okay? Usually it's an air-cooled pocket. Sometimes we use liquid nitrogen even to cool this, but it's a cooled pocket to make sure that we don't have anything that can come out or go in, okay? All right, then we take a power source over here, okay? We have a power source, and this power source, okay, is actually going to shock this, all right? So we're going to bring this in. We're going to come in here, okay? We're going to come across here, okay? We're going to put our sample. We're going to actually have our sample, whatever it is, okay? And if you can tell by definition, okay, you can tell by definition how much sample are we going to have. Well, we come over and we look. It's 1 gram of that substance. So we're going to have a 1 gram sample in our container here. And we're going to actually shock that. And what we're going to do is we're going to seal this off. Now we're going to make a really nice messy diagram here, so hang with us. So once we get our sample in, we're going to seal that off. Then we're going to fill this up with distilled water. Once again, distilled water is pure water, no ions. We're going to fill this up with distilled water. Now, the second thing we're going to do is we're going to put a thermometer in here, okay? So we're going to put a thermometer. All right? And then we're going to put a stirrer in there, something to circulate the water, okay? So then we're going to come down here. It looks like a little boat motor. Okay, and right here we're going to put a stirrer. All right? Now that stirrer is going to circulate the water. Now, then we're going to seal this thing up. We're going to make it airtight. We're going to fill this water all the way to the top. We're going to take the surface tension, we're going to come over the top, we're going to seal this thing off. So now we have a calorimeter, because now as we begin to shock this and we want to watch this, because we've got to watch how much we shock this, and once again our heat transfer formula comes in. So we can measure the mass of the water. We can determine how much the total water weighs that we put into this container. Then we check for the change in temperature. All right, the first temperature will be the initial. Okay, so when we do labs, so we have the initial and the final. So once again, we're going to take small I for initial and then small f for final. So we're going to start out with our initial temperature. We're going to go to our final temperature. We're going to subtract that and find out what the change in temperature of the water was. Then we're going to multiply that times the specific heat of the water. And then this is going to give us heat transfer. So let's take a look at this. Let's do an example. So let's say, for example, okay, let's say that we had 3,000 grams of water, okay, all right. So that fulfills our first requirement here, okay. So here's 3,000 grams of water. And then we do the change in temperature. We find the initial temperature and the final. We subtract those two, the final minus the initial, and let's say that it raised 3 degrees Celsius. Okay, so it makes a really easy formula. Now, here's the thing. Chemistry looks difficult. The math in chemistry is really not all that hard. It looks really difficult, but the thing is you have to understand what it is you're doing and what the application is. Remember, a chemist isn't trying to look impressive, or a chemist isn't trying to do anything. A chemist is trying to be practical. Okay, so here we go. So here's our formula. So we would have 3,000 grams times 3 times 4.18, and that once again is a specific heat of water, because we have to adjust for the water that's in the container. We have to adjust for the water that's absorbing the heat, that's showing us the temperature change. So we know that there's already 4.18 degrees Celsius in the specific heat of water that's already changing them. That's not part of the sample. So here we go. So 3,000 times 3 times 4.18. We just kind of did this pretty quick in our head, but we think it's going to come out. We got to look at this, because our answer, when we look at significant figures here, okay, even though this doesn't have one and this doesn't have one, we're saying that we didn't measure this one all the way out, but we're going to use these two decimal figures for our sig figs, our significant figures. So our answer is going to be 2 decimal places. So 3.76 times 10 to the 4th, okay. Now, this makes it interesting. We always come down to this because now we want to determine calories, okay. Now, the fascinating thing about this is, and we'll talk about this a little later as we go, okay, so this particular item here, okay, this particular item, because we came in with the 2 significant figures here, this particular item, whatever we put in there, actually had, it's kind of cool, 3.76 calories. How cool is that? So, once again, now it's a little more complicated than that when we go and actually figure calories, but remember, a calorimeter is used to determine calories, and the formula is heat of transfer. So, you'll need to know how to draw a calorimeter and do a sample problem like this, but once again, pretty easy if you understand how it works. So, feel free to email me if you have some questions, and just send back through Moodle questions, and we'll be able to answer those. So, that pretty well wraps up Unit 4, and I'll see you for Unit 5. Have a great week.